Okay, welcome to MAE 384, the first video of Module 1, where we will talk about round-off and truncation errors. After a first introduction, we are going to talk about decimal and binary numbers and how to convert them, so that by the end of this video, you will be able to convert binary numbers to decimal numbers. Okay, let's first talk about that term numerical method. It contains numeric, which basically means that we're dealing with measured or otherwise expressed items in numbers. So we're going to use numbers to measure and express things. And at its base core, it's a mathematical technique to solve problems. We can use this technique to solve problems even if they have no analytical solution, and that's why these numerical methods become very powerful and are widely used in engineering applications today. These methods that we will cover in our class are not limited to computers. They can actually be done by hand, and most of these methods were initially developed to be done by hand before the arrival of computers. The methods and the associated solution algorithms basically consist of a long series of simple calculations that are done one after the other. And these are often large and very repetitive simple calculations. So something that's perfectly done on a computer. And if they're done on a computer, we first have to talk about how do computers deal with numbers. And that involves how are numbers on a computer represented. In our everyday life, we are used to the decimal system, which has a base number of 10. So here's an example, the number 5,701.41. And we have a dot, a decimal point in this number that's marked here. And the position of the digits relative to that decimal point tell us something about the power of the base. And in this number, the base is just 10. That means that the first digit over to the left in 5,701.41, so the 1, is actually the digit that multiplies the 0th power of 10, so that multiplies 10 to the power 0, which is 1. The next digit over would multiply 10 to the power 1, so 10. The next digit over, 10 to the power 2, so therefore 100. The next digit, 10 to the power 3, 1000, and so on, all the way going to the left. So the further we go to the left of the decimal point, the power of 10 keeps on increasing. Now the first digit to the right of the decimal point multiplies the power 10 to the power -1, which is 0.1. And then the next digit over would be 10 to the power -2, and so on, going all the way. So let's do an example, a quick one here. So if we had the number 5,701.41, and we would express this as the sum of multipliers times powers of 10, this would be the following number. We have a 1 in the first digit to the left, so that would be 1 times 10 to the power 0. The next digit over is a 0, so plus 0. And this 0 multiplies the next power of 10, so that would be 10 to the power 1. The next digit over is a 7, so plus 7 times. And this digit multiplies 10 to the power 2. And then we have the last digit to the left, that is a 5, so this would be plus 5 times 10 to the power 3. And then there are zeros there, and we tend to not write these zeros when they're to the left of the largest non-zero digit. So let's move over to the right of the decimal point. So the first digit there is a 4. So we would have plus 4 times 10 to the power -1. And then the next digit is a 1, so plus 1 times 10 to the power -2. And then there are zeros there that follow that we typically don't write in the actual number, so we won't have to add them here. So this would be the number 5,701.41 expressed as a sum of digits multiplying the different powers of 10 of this number. Okay, so we've done this with the base 10 here as an example, which we're all familiar with. But this simple strategy can be employed to any other base. For example, a base 2 or a base 16. So which one should we choose if we deal with computers? Well, we have to look at how computers are built. And basically, computers at its core are built out of many individual switches or transistors that can have really only two different states. The switch can either be on, meaning it has a high voltage, or it can be off, meaning it has a low voltage. So we can store in a transistor one of two states, either a 0 or a 1. And that would mean, if we think about the base of our numbering system, that the base 2 would be ideal, because the base 2 only has two different states, a state 0 and a state 1. So therefore, computers actually represent their numbers in the binary system. All right, let's do one other example, since we're now in binary. So this number 1101.011, right? If I write this in the same strategy that I've wrote my base 10 numbers, I have a point. We can call this a binary point, because we can't really call it a decimal point anymore because we're now in the binary system. And the position of the digits relative to that binary point tells us the power of the base, as it was done in the decimal system, except that the base here is the number 2 and not the number 10. So the first digit to the left is the 0th power of the base, so 2 to the power 0. The next digit to the left would be increase the exponent by 1, so 2 to the power 1. The next digit over would be 2 to the power 2. Then comes 2 to the power 3, and so on. We always increase the exponent by 1 when we go over to the left. If we go to the right of the binary point, the first digit to the right would be 2 to the power negative 1. The next digit over, 2 to the power negative 2. The next one, 2 to the power negative 3, and so on. We would continuously decrease the exponent by 1 for every digit that we go over to the right. So let's do this number here, 1101.011, and express it the same way as we did a decimal number, as the sum of a digit multiplying its corresponding power of 2. So if we start with the first digit to the left of the binary point, the digit here in the number is a 1. So this 1 here multiplies the power of 2, which is 0, so times 2 to the power 0. The next digit over is a 0, so we can write plus 0 times 2 to the power 1. The next digit over is again a 1, so plus 1 times 2 to the power 2. And then the next digit is again a 1, so plus 1 times 2 to the power 3. And we don't have any digits further to the left of the binary point, so we can stop the sequence here going to the left. But we have digits to the right of the binary point, so we have to take those into account as well. So the first digit to the right of the binary point is a 0. So we have plus 0 times the power of 2 associated with the first digit to the right of the binary point is 2 to the power negative 1, so times 2 to the power negative 1. The next digit over is a 1, so plus 1 times 2 to the power negative 2. And then the last digit we have in this number is again a 1, so plus 1 times the associated power of 2 is 2 to the power negative 3. Okay, so this number now we can write as a decimal number if we do the individual math steps. So the first thing over here is a 1 times 2 to the power 0. 2 to the power 0 is 1. So we have a 1 times 1 plus a 0 times 2, that's just 0. Then we have a 1 times 2 to the power 2, so that's 4. Then we have a plus 1 times 2 to the power 3, so that's 2 to the power 3 is 8, so plus 8. Then 0 times something is 0, plus 1 times 2 to the power negative 2. So that would be 1 over 4, so that would be 0.25. And then the last digit is 1 times 2 to the power negative 3. That's 1 over 8. That is plus 0.125. So if we add these numbers together, a 1 plus a 4 is a 5, plus an 8 is a 13, plus a 0.25 and a 0.125, that would be 13.375. So that would be the binary number 1101.011 expressed as a decimal number. Okay. This is basically the strategy how to convert binary numbers into decimal numbers. You find out the powers of 2 that each digit multiplies, and then you just express and sum up the resulting sum and find the corresponding decimal number. In our example, that came out to be the decimal number 13.375. Okay, so in this video, we've done a brief introduction. And then we've looked at how decimal and binary numbers are converted, how we go from a binary number to a decimal number specifically. And in the next video, we will look at how we do the reverse. How can we convert a decimal number to a binary number? Thanks for watching.